Hello friends, welcome to the mathematical room. I am the caretaker Lucifer. So today we are going to start ring theory from Herstein's topics in algebra. Now this is the third chapter and this series of videos is going to assume that we have already gone through the group theory portion of Herstein's algebra. Since I have not actually done that, I have planned to do that alongside this in the form of videos on group theory from that same book. So some references to group theory results that we will use here will strictly speaking will be incomplete because we don't have group theory yet. But if we go to the group theory videos which are coming soon, there all the explanations will be available. So with that, let us now start. Now groups arise from this example. There are many instances of groups in mathematics and outside mathematics, but more or less every such example can somehow be understood in terms of this example. If we are given a non-empty set, then we can consider bijective functions on that set, that is one-to-one onto functions on the set. The collection of such functions forms a group with respect to the composition of functions. Rings, however, stem from a more familiar source, namely the system of integers, which Herstein denotes by J. In the popular literature, it is, in the mathematical literature, it is denoted by blackboard bull Z, okay, or Z. Now, we will see that rings are actually generalizations of the algebraic properties of ordinary integers, direct generalizations. Now there is a very important difference between groups and rings. Each group has only one binary operation defined in it. However, we will soon see that rings are two operational systems. There are two operations known as addition and multiplication. But despite this difference, we will see that the concepts of homomorphism, normal subgroup, factor groups, those things, for them we will find analogs of those things in rings, and the study of rings will follow the pattern already laid out for groups. Like we will have homomorphisms of rings, then we will have some analog of kernel of a homomorphism, we will then have homomorphism theorems. So those things we will do similarly. Now with that, I should add that although this thing, just like groups, at first will seem very arbitrary and abstract, but later on in this book we will see that the results derived in this and in some coming other chapter, they have applications in proving some things with which we are already familiar. And one of them is geometric constructions. You recall from your school days that we have done constructions in Euclidean geometry, where we are given straight edge and compass, and we are to construct some things, some figures. Say we have to bisect an angle, we have to draw a perpendicular bisector to a line, so that sort of things. Now, using the results of ring theory, or rather the results of field theory, fields are special types of rings, we will at one point prove this. It is impossible to trisect an angle of 60 degrees using only straight edge and compass. So this geometric result can be proved using results from field theory, particularly the theory of algebraic numbers. Okay, so those things will come. So let us now start with the definition of rings. Ideally, such an abstract thing should not start with the definition. It should start with examples, with things that with which we are already familiar. Then from those examples we have to motivate an abstract definition, and there should be some actual compelling reasons for making such definitions. But since we have assumed here that we have already gone through Herstein's group theory, so those type of considerations have already been made for groups. So here we start with definition. Okay, so here is the definition of a ring. A non-empty set R is said to be an associative ring if in R there are defined two operations plus and dot known as addition and multiplication, such that for all elements A, B and C in R, the following axioms are satisfied. The first one is A plus B should belong to R. The second one is A plus B should be equal to B plus A. And the third one is this. The fourth one, there is an element 0 in R such that A plus 0 equals A. Fifth one, there is an element minus A in R such that A plus minus A equals 0. The sixth one, A dot B. Now we come to the second operation. A dot B is in R. The seventh one says this. We are saying first one, second one, but the order really does not matter. Although we should not write them arbitrarily in any way we want, but some of the orders can be changed. For example, you can write this one here, this one here. the eighth one involves both the operations a dot b plus a dot c and b plus c dot a equals b dot a plus c dot a. Okay. Now, there are some comments that have to be made about these axioms. But those comments I will make sketchily because of that assumption that we have already gone through group theory. So we have some experience with this sort of axioms, algebraic axioms. The first axiom is a closure property. It says that, or this is expressed by saying that R is closed with respect to the operation addition. In applying this operation, or the operation does not let us outside of R, it keeps us inside R. No matter how many times we operate two elements using this operation, we are going to get again an element in R. Okay. Now, although there is no need to say this, but still, let us just quickly recall what this thing actually, strictly speaking, means. You see, these operations are by definition functions which look like this. Which are, each one of them is a function from the ordered pair R cross R, from the Cartesian product, sorry, I said ordered pair, from the Cartesian product R cross R into R. And A plus B by definition is the value of this function plus at the ordered pair A comma B. Just like that, A dot B means the value of the function dot at the ordered pair A comma B. For simplicity, we write these functional values like this. That's what they are. Okay. Now, these operations are called binary operations because they involve two things from R. If they involve three things, they will be called ternary operations. Those things are also available in algebra. Maybe in future we will come across them somewhere. Not only in algebra, but they are available nonetheless. So this is the closure property. R is closed with respect to addition. This you already know. It says that addition is commutative. This one says that addition is associative. This one says that R has an additive identity. Okay, if I use group theoretic terminology, this is an additive identity. In this context, in the context of rings, this is called a zero element. Okay, let me write it here. A zero element. And for the fifth one is that for every element A in R, there is a negative. Okay, we call this the negative of A in R such that their sum is 0. Since the operation is commutative, I have not written alongside this is equal to 0 plus A, because A plus 0 equals 0 plus A. That follows from this commutativity. Similarly, here I have not written equal to minus A plus A. That follows from commutativity. Okay. Now the sixth operation, just like this one, sixth operation I say, what am I thinking today? The second operation, R is closed with respect to the second operation. I am at a loss for words today. I don't know why. Okay. please bear with me. R is closed with respect to the second operation, multiplication. Just like this one, the seventh one says that multiplication is associative. And these are the distributive laws. This is the left distributive law, this is the right distributive law. I can say this or express this by saying that multiplication distributes itself over addition from the left, and multiplication distributes itself over addition from the right. Okay, so these are the meanings of these things. Now now if we think of these axioms in terms of group theory, then you can see that axioms 1 through 5 merely state that R is an abelian group under addition. Okay, it just, the first 5 axioms say that R is an abelian group under addition. Axioms 6 and 7 say that R is closed under an associative operation dot, which is multiplication. Okay, this is dot, this is full stop or period. So the 6th and 7th one say that R is closed under an associative multiplication. Axiom 8 interrelates the two operations. When we work with, in algebra, when we work with, not only in algebra but elsewhere also in mathematics, when we work with multi-operational systems, like here we have 2 operations, there are some systems which may have even many other operations, okay. Some of them behave like this, some other operations may behave entirely differently. But in all of them, we will see axioms like this, which link the operations to one another. Why? It's because if there is no axiom 8, then the operations addition and multiplication are not interacting with each other. So what is the point of keeping them together in a system if this part does not interact with this part? Okay, they will become 2 separate systems with no relation at all, since there is no interaction. That's why to make those type of interactions possible, we impose this additional restriction. In this case, similar restrictions we will see when we go further into algebra. Right. Now one point, yes. For us, rings, the word rings will mean associative rings. Note that we have actually defined associative ring, and this associative comes from this axiom. The second operation is associative. From there, this thing comes associative. Non-associative rings that is systems where axiom 7 may fail to hold do occur in mathematics and are studied. But we shall not consider them here. Okay. Now we have the definition of a ring. Now there are some special conditions which, if they are true, we have special types of rings. It may or may not happen that there is an element 1 in R. This is not number 1. Okay, it's an element that is going to behave like 1. For that reason, we denote it by the symbol 1. But often this type of things create confusion in algebra. More of this will be discussed when we start group theory. Okay, there will be a discussion at length about such confusions which arise because of this sort of what can I say, simplicity of notation. At first there is confusion, but later on when we become well accustomed to the things, then there is no confusion. Okay. Anyway, this is an element. If there is an element 1 in R such that 1 dot A equals A dot 1 equals A. It may happen that there is one such element. If R has such an element, then we say R is a ring with unit element and 1 is a unit element. Okay. If now this is a class of rings. Some rings have such elements. Okay, they are said to be rings with unit element. Now there is something else. If A dot B equals B dot A for all A and B in R, that is, if the second operation, multiplication, is commutative, then R is said to be a commutative ring. Naturally, these two conditions are independent of each other. Okay. In a ring, neither of them may be true, or exactly one of them may be true, or both of them may be true. Okay. They don't have any causal relationship to each other, that if one of them is true, then the other is a consequence. It's not like that. It will become clear when we see the first few examples of a ring. Right. So let us now go to the examples. Example 3.1.1. Here, however, Herstein decides to number the examples properly, but definition he does not care. Okay, so the first example is naturally going to be the system of integers, because we have said that from there only things are arising. So let R be the set of all integers plus B the usual addition and dot be the usual multiplication. Of integers. Okay, then R is a commutative ring with unit element. Most often this is casually mentioned without any proof, but since in our videos on analysis we are going to prove this thing, so I am going to refer to that result, which we have not done yet, but we will soon do. See proposition 4.1.6. That is from Tau's analysis. Right now we are going through axiomatic set theory in real analysis. Once that chapter is over, we will use its results to axiomatically construct the system of integers. There we will actually prove the properties that addition of integers is commutative, associative, all those things will be proved. And that precisely that result, that the integers form a commutative ring with unit element, that is this proposition 4.1.6. So when we prove this, there we will see everything. Then example 3.1.2. Let R be the set of all even integers which are divisible by 2. R is a commutative ring under usual addition and multiplication of integers that has no unit element. Okay, now I leave it to you to prove that this is the case, that the set of even integers is a ring with respect to usual addition and multiplication of integers, and there is no unit element. Actually, the fact that there is no unit element follows from this proposition. Proposition 418. See, we should, although these things look very natural and we already know them, but nevertheless they need proof. They should not be taken lightly, because these systems, it takes a lot of effort to actually construct them from scratch. So the properties that they satisfy the ring axioms, they are also in a sense non-trivial. That's why I am mentioning that proposition. This proposition says that the ring, this particular ring, does not have a unit element. When we see this proposition, we will understand why. But the other thing, that it forms a commutative ring, that I leave that to you. But keep in mind that every step that you show that addition is commutative should have a solid logical justification. You can use the fact that in example 311, the set of integers forms a commutative ring with unit element under usual addition and multiplication. This fact can be used to prove this, but the proof should be complete. Okay, so I leave that to you. We now see the third example. Let R be the set of all rational numbers. R is a commutative ring with unit element. Here also there is a proof, because after constructing the system of integers in our analysis videos, we will also construct, using them, the system of rational numbers. There we will prove all the basic properties of rational numbers from scratch or from that construction. Okay, so I am referring to the appropriate result C proposition 424. This particular result says that the system of what is this? Rational numbers is a commutative ring with unit element. But that is not all, as you all may already know, but more is true. the non-zero elements of R form an abelian group under multiplication. A ring with this latter property is called a field. Note that a ring by definition is an abelian group with respect to addition. But if the non-zero elements in the ring form an abelian group with respect to multiplication, then we say that the ring is a field. This ring is a field, the ring of rational numbers. Okay, so the fact that it is a field, I think the entire thing is given in this proposition, not merely the fact that it's a commutative ring with unit element. Then we come to the fourth example. Okay, this one is, I think it is 7, right? Yes. Let R be J7. We already know what J7 is, right? It is the set of integers modulo 7. So it is the collection of all or the